Welcome, students. Today, let's explore cylinders, shapes you encounter almost every day, like tins or pipes. Think about how these shapes form. The curved surface comes from rolling a flat rectangle such that its opposite edges meet to form a circle. This means the length of the rectangle equals the circumference of the circle on the ends. Visualize a flat sheet being wrapped around to create the smooth curved surface connecting two circular bases. This insight connects flat two-dimensional shapes to three-dimensional solids, the core of solid geometry. How might the size of the rectangle relate precisely to the circular base? I'll guide you through this step by step. Keep this curious mind ready, and let's jump into the details. Let's understand the surface area of cylinders better. Imagine cutting a cylinder vertically along its height and unrolling its curved surface. This curved surface becomes a rectangle. One side of this rectangle matches the height of the cylinder, and the other side equals the circumference of the circular base, which is 2 times p times r. So, the curved surface area is just the length times the width of that rectangle, which is 2 pi r times h. Adding the areas of the two circular bases, each pi times r squared, gives the total surface area. That is, 2 pi r squared plus 2 pi rh. Let's try a mental question. If you have a cylinder with radius 7 centimeters and height 10 centimeters, can you calculate its curved surface area using this formula? Take a moment to think and try. This understanding of flattening curved surfaces into rectangles is a powerful way to tackle complex three-dimensional shapes. Let's apply the total surface area formula in a real-world example. Suppose we want to find the surface area needed to paint a cylindrical tank with radius 14 centimeters and height 8 centimeters. Our given values are r equals 14 and h equals 8. Using the formula 2 pi r times open bracket r plus h close bracket, our first step is to calculate 2 pi r. That is 2 times 22 divided by 7 times 14, and this equals 88 centimeters. Next, we add the radius and height. 14 plus 8 equals 22. Multiplying 88 by 22 gives us 1,936 square centimeters. So, the total surface area of the cylinder is 1,936 centimeters squared. This means you'll need enough paint to cover roughly 19.36 square meters if you convert to meters squared. Why is understanding surface area useful? Think about the cost if paint is sold per square meter. The more surface area, the more paint you'll need. You're doing fantastic engaging your spatial reasoning here. Let's shift our focus to volume, one of the most important concepts in geometry. Volume tells us how much space an object occupies. Imagine filling a box with tiny cubes. The total number of these cubes equals the volume. For a cuboid, which you can think of as a rectangular box, the volume is found by multiplying its length, breadth, and height. Symbolically, volume equals length multiplied by breadth multiplied by height. For a cube, all sides are equal, so the volume is just one side length cubed. Suppose a cube has sides measuring 3 units. The volume would be 3 to the power of 3, which equals 27 cubic units. This method of counting unit cubes helps you visualize why we multiply dimensions. Let me ask you, how would stacking one flat sheet multiple times relate here? The height changes, but the base stays the same. This intuitive idea helps understand volume calculations practically. Keep this in mind as we move to related examples. Let's work through an example to find the volume of a cuboid. Suppose the length is 12 units, the breadth is 3 units, and the height is 1 unit. Using the formula, volume equals length multiplied by breadth multiplied by height. First, we multiply 12 by 3 to get 36. Then, multiplying 36 by the height, which is 1, leaves the volume still 36 cubic units. This means the cuboid occupies space equal to 36 unit cubes. Let's think together. If we double the height, the volume doubles as well. Try to visualize this by imagining stacking identical cuboids on top of each other. This stepwise approach to volume helps you grasp the effect of each dimension on the object's size. Keep practicing this pattern to master volume calculations. Now let's find the volume of a cube, whose sides are 4 centimeters long. The formula for the volume of a cube is the side length cubed. So, we calculate 4 times 4 times 4, which equals 64 cubic centimeters. Imagine a box made up of 64 tiny cubes stacked together perfectly. Understanding cubes is fundamental because many objects are cube-shaped or close to it, and their volume calculation is straightforward. Fun fact, cubes have all faces equal, making their surface area simpler to calculate. How do you think doubling the side length would change the volume? Pause and try to compute the new volume. This is a great mental exercise to understand scaling in three-dimensional shapes. Let's explore the volume of a cylinder now. Remember how we used the area of the base and multiplied by the height for cuboids? The same principle applies for cylinders. The base of a cylinder is a circle, so finding its area involves pi, multiplied by the square of the radius. Multiplying that area by the height gives us the volume. Think of filling the cylinder with tiny circular discs stacked completely to the top. This gives a practical image of volume as the space occupied. Imagine a water tank shaped like a cylinder. Knowing this formula helps calculate how much water it can hold. Remember, pi is approximately 3.14, but we often use 22 divided by 7 as a common fraction approximation. I encourage you to try this formula with your own measurements. Let's apply our cylinder volume formula to a real example. Given a cylinder with radius 20 centimeters and height 14 centimeters, we begin by squaring the radius. 20 times 20 equals 400. Next, multiplying pi, approximated as 22 over 7, times radius squared, times height, we calculate open bracket 22 times 100 times 14 close bracket divided by 7. This equals 17,600. So, the cylinder's volume is 17,600 cubic centimeters. Imagine filling this cylinder with tiny 1 centimeter cubes. It would take 17,600 of those to fill completely. This formula and method are vital in fields like engineering and packaging, where space optimization is key. What if the radius was half? Can you guess how the volume would change? Think about it. Here is a creative example showing the link between two-dimensional and three-dimensional shapes. A rectangular paper of 11 centimeters by 4 centimeters is rolled along its length to form a cylinder. That means the length 11 centimeters becomes the perimeter of the base circle. Solving the equation 2 pi r equals 11, we find the radius to be 7 divided by 4 centimeters. The height, being the width of the paper, is 4 centimeters. Now, using the volume formula for cylinders, which is pi times r squared times h, we substitute the radius and height and calculate. This simplifies to approximately 38.5 cubic centimeters. This problem beautifully connects the idea of unfolding and folding shapes and shows practical geometry. Can you picture rolling any rectangular sheet to form cylinders? Let's consider a practical architecture-related problem. There are 24 cylindrical pillars, each with a radius of 28 centimeters and a height of 4 meters. If painting costs 8 rupees per square meter for the curved surface area, what will be the total cost? Converting the radius to meters for consistency. r equals 0.28 meters. We calculate the curved surface area for one pillar using 2 pi rh. This yields approximately 7.04 square meters. For all 24 pillars, multiply 7.04 by 24. This gives 168.96 square meters. Now multiplying by the cost per square meter, 168.96 times 8 gives approximately 1,351 rupees and 68 paise. So, painting all pillars will cost you 1,351 rupees and 68 paise. This application connects geometry to real-life budgeting and planning. Can you see how surface area directly impacts cost? Here's a problem that requires algebra to find the missing dimension. Given a cylinder with radius 7 centimeters and total surface area 968 square centimeters, we want to find its height. We use the total surface area formula. 2 PIR times open bracket r plus h close bracket equals 968. Substituting the values, we get 2 times 22 divided by 7 times open bracket. 7 plus h close bracket equals 968. Simplifying, this becomes 44 times open bracket, 7 plus h, close bracket equals 968. We divide both sides by 44 to get 7 plus h equals 22. Finally, subtract 7 from both sides, leaving h equals 15 centimeters. This shows how understanding formulas and algebra work hand in hand. Don't be intimidated. This is a step-by-step problem, where breaking down equations helps solve unknowns. You might wonder, what is the difference between volume and capacity? Volume is the physical space a solid occupies. Capacity, on the other hand, is commonly used for containers, and it tells how much liquid they can hold. For example, a water tin holding 100 cubic centimeters of water has a capacity of 100 cubic centimeters, or 100 milliliters. This is because 1 cubic centimeter equals 1 milliliter. Also, remember that 1 liter equals 1,000 cubic centimeters, and 1 cubic meter equals 1,000 liters. This knowledge is crucial for everyday life. Think about buying a bottle of water or measuring fuel. Moving from geometric volume to practical capacity connects math to real-world usage. Try converting between these units yourself. It is a handy skill. Let's link volume to practical storage problems. Imagine a go-down, which is a storage warehouse that is 60 meters long, 40 meters wide, and 30 meters high. The total volume is 60 times 40 times 30, which equals 72,000 cubic meters. Each cuboidal box has a volume of 0.8 cubic meters. How many such boxes can we store? Dividing the go-down's total volume by the volume of one box, we get 72,000 divided by 0.8, which equals 90,000 boxes. This calculation assumes perfect packing with no wasted space, but it gives a good idea of capacity. It shows how understanding volume helps in space planning and logistics. Can you think of other contexts where you would use such computations? Let's review what we have learned today. Surface area tells us the total area covering a faces of a solid. For cuboids, it is 2 times the sum of length multiplied by breadth multiplied by height, and height multiplied by length. For cubes, it is simply 6 times the side squared. And for cylinders, it is 2 times pi times r, multiplied by the sum of r plus h. Volume is the space enclosed inside an object. For cuboids, multiply length, breadth, and height. For cubes, it is the side cubed. And for cylinders, it is pi times radius squared times height. Remember, understanding volume and surface area formulas lets you solve real-world problems, from designing containers to space planning. Also, volume measurements connect to units like liters and milliliters, which are vital in practical scenarios. Remember, using these formulas correctly and knowing unit conversions will empower you in math and beyond. Keep practicing, and soon these concepts will become second nature. Great job staying engaged throughout.